Elena. 55.
Yeah, then we get in the 100.
Say it says find equations of both lines that are tangent to the curve y equals 1 plus x cubed, and also parallel to the line 12x minus y equals 1. So I'm going to use, I know that parallel lines have equal slopes, right? Thanks, Bill. So I'm going to take my equation and figure out the slope from this. So we'll subtract the 12x from both sides and then divide by -1. So I know the slope I'm looking for is 12. Okie dokie so far? So now I'm going to take this, and I need the derivative if I'm going to talk about the slopes. So what's the derivative of 1 plus x cubed? 3x squared. 0 plus is fine. Yeah, like same thing. And so I'm interested in when that derivative is equal to 12, the slope. So I divide both sides by 3, and then I square root both sides, and I get x is plus or minus 2. Okay with that so far? So when x is -2, y is going to be 1 plus -2 cubed, so -7. And when x is +2, the y is going to be 1 plus +2 cubed, 9. So my two tangent lines are going to be y minus -7 equals 12 times x minus -2. And then y minus 9 equals 12 times x minus +2. That's it. I'm done. So the hard part of this was like figuring out what I needed and where am I going to get it from, right? So I got the slope from the number for the slope from the line that we had to be parallel to, because I know that the parallel lines have to have equal slopes. I used that slope number, plugged it into the derivative to find the x coordinate in my function, and then to get the y coordinate, I plugged that x coordinate into the original function to get the y coordinate. And then I just had my slope and my point, so point-slope formula. Does that feel okay, Elena? And again, nothing we did there was like super duper tricky, right? In fact, there's only like one little piece of calculus to it. The rest of it was kind of like algebra 1-y. But like, you really had to understand what was going on to move effectively between all the information that you're given, so you could get the pieces that you needed. Who's next? Pierce, did you say you had one also?
Oh, no, that was a joke.
Oh, okay. Yes. Is this related to the one we're doing right now?
Oh, no.
No? Isabel?
Can you do number
27? Sure.
Mr. Blue?
Yes.
Can I use graph real quick?
Oh, yeah, absolutely. Of course. Okay, so just asking for the derivative of h of x. As it's currently written, I cannot do the derivative of this because what I have is a composition of two functions, right? I have this x plus 1 over x inside of like x cubed. We don't know how to do that yet. Give me It'll be like the first topic we do after the test. But we don't know how to do that yet. What do I need to do instead then? I need to FOIL that out. So you may remember like our perfect cubes multiplication pattern is this. So if I use that, I have cubed 3x cubed x to the negative 1, 3x x to the negative 1 squared plus x to the negative 1 cubed. Or if I simplify this all down, x cubed plus 3x plus 3x to the negative 1 plus x to the negative 3. And now I'm in a spot where I can do the derivative just using the rules that I have available to me. Because I've removed the composition piece, right? I don't have one function inside of another. I just have 4 things in that form of the power rule. So my derivative of x cubed, just like we said before, 3x squared. The derivative of 3x is 3 times 1. The derivative of 3x to the negative 1 is going to be negative 1 times x to the negative 2, or 3 times negative 1 times x to the negative 2. And then the derivative of x to the negative 3 is going to be negative 3x to the negative 4. And probably the way the answer in the back of the book would look is we would probably rewrite this with no negative exponents. So it'd probably look like that in a multiple choice setting or in the back of the book. But in a free response setting, I wouldn't be so picky about that. But we should just be aware that, like, on a multiple choice setting, or if you're looking something up in an answer key, they're going to give you like an answer that looks like that as opposed to with negative exponents. Isabel, does that feel okay?
Yeah.
Pierce.
Could you do 31, please?
Sure. Okay. So again, I have an issue here because I don't have something with a negative exponent on it, or with a power rule form, because I have it in the denominator. So I'm just going to use my rules of exponents to do that. So far, so good. So now I'm ready to take the derivative. So that's going to be dz dy. And the a stays out front because it's just a constant. So I'll have negative 10 y to the negative 1. The b is just going to stay out front because it's a constant. And then the derivative of e to the y is just e to the y. So when I simplify this down, we would probably write it as negative 10a over y to the 11th plus b e to the y. So those constants, the a and the b, look scary, but like I just treat them the same way with like a number. I just kind of ignore them and just they stick around, but it's fine. Isabel?
So for that, like, if we didn't write dz over dy,
If you wrote z prime, that would be acceptable. Talika.
could you do 7?
71. Yeah, of course. Okay, we want to find the equation of the parabola y equals ax squared plus bx, whose tangent line at 1, 1 has the equation y equals 3x minus 2. So I have two variables to solve for, a and b, right? Okay. Well, I know that y prime of 1 has to give me 3. Why do I know that? Yeah, so the slope when x equals 1 has to be 3, right? And I know that y, so when I know that y of 1 has to give me 1. Because the x, when x is 1, y is 1, right? This is going to be my system of two equations that I'm going to use to solve for a and b. So y prime is going to be 2ax. I should say, instead of x, though, it's going to be 1. And then plus b, and that has to equal 3. And then y of 1 is going to be a times 1 squared plus b times 1 should equal 1. And now I'm just going to solve the system. So how would I solve this system? I'm going to put in a matrix and use RREF on it because I don't really want to grind out the substitution or elimination to do this. Because it's like too early in the morning for Mr. Kulik. So make a 2 by 3 matrix, coefficients 2, 1, 3, and then we have 1, 1, 1. Get back out of there. Go back to the matrix menu, pick math, and then go down to RREF on matrix A. And bada boom, bada bing, A is 2, B is negative 1. So we'd have y equals 2x squared minus x. Ought to do us. So again, it's one of those things like recognizing that, okay, I need a and b, probably going to have to solve a system because there are variables in the same equation or unknowns in the same equation. How can I get an equation with a and b in it? Well, one of them for a, or one of them should be obvious because I have the point. So that's just fill it in the x and y. There's one equation with a and b. And I have the derivative at x equals 1. So again, I have an input and output. So that's my other equation. Isabel. 29. Sure. I think that's a 5 up there, isn't it? Okay. So again, first order of business is to put this in a form where I can use my power rule. And the key here is remembering that, like, that rule from Algebra 2. So now if I do this, I'd say du dt, where u prime would be fine also, is 1/5 u to the negative 4/5 plus 4 times 5/2 t to the 3/2. And then if I were to put this in the form I'd expect, I would have 1/5 5th root t to the 4th plus, 10, and then the square root t cubed is probably what I would expect to see there. Does that feel?
Yeah, that makes sense. I don't know what I did wrong, but got it.
Yeah, so again, typically the hard part is the algebra pieces. Like, how can I rearrange this into a form where I can just apply the power rule? And once I've applied the power rule, how would I rearrange this back to a form that like is going to look the same way as the back of the book's answer, or like the multiple choice answer? Usually the calculus piece, not hard. It's the algebra before and after that kind of can be the tricky parts. Because we've just gone and made the calculus part real easy with these new shortcuts, right? Okay. Last call on questions here. Elena.
Could you do 7?
Sure. Yeah, of course. 75. Oh, this is a good one, I think. Okay. So it says, find the values of m and b that make f differentiable everywhere. So when we say differentiable everywhere, what things do we need to make sure or what things need to happen to ensure this is differentiable everywhere? There are 3 things. You'd have to know this for the test. I need continuous. Gotta have that. So guess what? All these ideas of continuity from last chapter, do I still need all that stuff? You betcha! What else do I need? No corners. No sharp corners. No place where the slope is going to transition from like 2 to 3 instantaneously, right? We can't have a derivative at a corner. And the other is no vertical tangents. Those are the 3 things that we have to have for differentiability everywhere. So you have to be continuous. You can't have any gaps, any jumps, any removables. And then we can't have any corners, and we can't have any vertical tangents. So of these 3 things, which are the 2 that I would need to worry about for this problem? Continuity for sure. No, it's the corners. On a piecewise function, if one piece has like a constant slope coming in and the other piece has a constant slope coming in, that's where you're going to get a corner. For a piecewise function, you're not going to get a vertical, the graph isn't going to look vertical someplace unless one of our functions makes it look vertical, right? But x squared never becomes vertical and a linear never becomes vertical. So I'm comfortable with just worrying about those 2. Everybody's good with that? So for the continuity piece, do I need to worry about f or the derivative of f? No, just f. So the continuity piece all has to do with f, because if f is continuous, we need f to be continuous to at least have the possibility of differentiability, right? If you have a discontinuity, we know we're not differentiable there, right? But continuity is all about the function, not about the derivative, right? So what do I need to show for continuous? You need to know this definition. This is not one that we can forget because it comes up all the time. So we say f is continuous at a if f of a is equal to the limit as x approaches a of f of x, right? That's our definition of continuity. You must remember this. It comes up frequently across multiple chapters. These continuity is important when doing calculus because it works a lot better on continuous things than discontinuous things. Okay? So f of a, well, that's really easy. In this case, what is the a that we're concerned with? 2. Why am I only concerned with 2? Because this is a polynomial. It's continuous over its entire domain. This is a polynomial, continuous over its entire domain. The only place where we have to worry about is making sure those two functions meet. The end of one is the start of the other. Everybody's okay? So f of 2 is just going to be 2 squared. That's 4. And then to show the limit as x approaches 2 of f of x, well, this we can't do directly. Why not? Because we don't know if the function is continuous at 2, right? We can't assume that because that's what we need to figure out the m and b to make it so. So if I don't have continuity and I have I don't have a direct substitution situation and it's piecewise, what do I have to look at? I have to look at the left-hand limit, which that is going to be 4. And then I have to look at the right-hand limit, which is going to be m times 2 plus b. So for us to be continuous, one of the equations in my system has to be 2m plus b equals 4. Everybody's good with that? So I'll have continuity if 2m plus b is 4, because then my definition of continuity applies. Everybody good with that? Okay. Now, if I'm looking at corners, should I be looking at f or f prime? F prime. Good. And how do I check that? Well, it's not something I can graph because the linear function is m plus b, so I can't actually graph that, right? Oh, what do I want to say? No, let's not say that. Let's say this. This is really what I want to check. Right? So I want to check that at every a, the limit from the left for the derivative is equal to the limit of the right for the derivative. So they're both approaching the same value, which means that like you're going to have a smooth curve coming in rather than like where you have an abrupt change. Okay, so how do I take the derivative of f if it's a piecewise function? I just take the derivative of pieces. What's the derivative of x squared? Okay. Yes, GG. Uh-huh. And what's the derivative of mx plus b? M. Okay. So I need then the limit as x approaches 2 from the left of 2x to equal the limit as x approaches 2 from the right of m. Or in other words, m has to be 4. Oh, well, that's a really easy system to solve then. So 8 plus b has to be 4. So b has to be negative 4. And that ought to do it. Did that match the answer in the back of the book? Radical.
That's a lot.
Look, here's the thing. Here's the thing. I spelled out like every single detail on how to do this. This is something you should be able to do quite quickly. Because look at in the end of the day, what did we do? We've made sure that the two functions met, or the two pieces met at the same point, and then the derivatives met at the same point. Right? Or I should say the limit, the left-hand limit and the right-hand limit at that point where they meet was the same. That's all we checked. This is a super, super common question, either from a multiple choice standpoint, where they may just give you a piecewise function, ask where is it differentiable, or where is it not differentiable? And this is exactly what you check. You have to check first, is it continuous? So you just need to check to make sure at each of the gaps you have continuity, which is easy, right? Like all I did was just basically plug numbers in to the left side and the right side to make sure they matched. And then I need to check for the corners, which again is easy. All I did is take the derivative, plug in the left and right side and make sure they match. That's all I'm really doing. I could have done this in my head, conceivably, particularly if this was numeric, right? But a question like this is not an uncommon free response question. Like find the m and b that would make this differentiable everywhere. Very common format for a free response question. This is a good one.
Would you put this on the test?
Absolutely would put something like this on the test. Absolutely would.
Really?
Yeah. This is absolutely the kind of question that like I think is an important one to ask. I think the AP thinks it's an important one to ask. Whether it's as a multiple choice question or as a free response question, I think this is a good one.
Can we go over the few or
review, like, we just do everything that you have us review.
Well, here's what I've already put the stuff up here already. So if you want to look at this, so I have like this stuff, the stuff to look over again, but I also made a multiple choice practice stuff for you on the IEP. I have the same multiple choice questions here if you'd like to do them where it's a little bit easier to write stuff down. But I made like just multiple choice practice. And I have free response practice.
So this will be similar to the ones we had.
Yeah, so this will be similar to things I would ask you to do on the test for sure.
Similar, like, is that not really similar, like, that word?
Yes to both. But I think like it would be foolish not to do these things. In fact, that's what I have planned on Fridays. Just like we'll talk about test format, but I'd rather have you spend some time just like working on multiple choice questions or working on these free response questions by yourself or with someone else or whatever. Totally fine. But I think that would be a really good use of our time. Okay. 3, 2. Let's do 3, 2 then.
Why?
So first thing is called the product rule. The product rule is going to allow us to take the derivative of two functions multiplied together where I cannot simplify them into just one function, right? So if I have x times the square root of x, I don't need to use the product rule on that. I can just use algebra and then the power rule, right? But if I have x times e to the x, there's no algebra I can do to get those x's into one place. That I would have to use the product rule on. And what the product rule says is the derivative of f of x times g of x is the derivative of g of x times f plus the derivative of f times g. Yeah, I mean, it's just, I just read what's here.
It just helps.
Yeah, so it's f times the derivative of g plus g times the derivative of f is the way they have it written down. How are we going to prove this? What's up?
We put numbers into it just for the.
Yeah, we'll do a specific problem examples in just a second. Absolutely. But how would I prove this?
Take the derivative of the actual thing. And do it that
Nope. I use the definition of a derivative, aka we're doing limits. Just to prove it. Just to prove it. Not to do it,
way. I believe you, though.
to prove it.
Like, I trust you, Mr. Kulik. You don't have to. You don't have
This is, let me tell you something. For a group of kids that's probably going to take like college calculus courses, you are, I would say, at least 50% chance that you run into a professor that is wholly uninterested in numeric problems and wants everything to be a proof. And will spend all, because, hold on. You ask why? Because that is the point of higher level mathematics. We're unconcerned with doing problems and wholly concerned about proving new things. And you will run into, if you take enough math classes, you will run into a professor where even a majority of your problems in a new, possibly course like this that's very numeric, are just like, I've picked only the proof problems out of the homework set for you to do. And you run in, so and again, I don't guarantee that this will happen, but it's a realistic possibility. And I want to give you some of that now, so that it's not an abrupt, like, this isn't math. Why didn't we ever do any math or any proof in high school? I wish I would have done more of this in high school. I wish I would have seen some of this before. So I'm trying to cover both grounds, okay? And I know that the proof is difficult, and it feels like, what's the point of doing this? I believe you. The point is that, like, that is the point of mathematics, is to prove new things, okay? And I don't mean to, like, I'm not trying to be mean. I don't want to sound mean about it or whatever, but like, that is what we're trying to do here. Okay. So again, I should have picked a different function name than h, huh? Let's call it k. Because I have h's other ways. That's bad notation, Mr. Kulik. Okay, so I'll go ahead and evaluate h of x, which is f of x times g of x. Okay, so far so good. No? What is going to be the trick here? It's okay. I'm going to add or subtract and then add this quantity, which is the same as doing nothing at all, right? If I just subtract it and then I add it back. Everybody's okay?
Wait, actually, get the f of x plus h down to g of x.
I picked it. Well, I subtracted it, and then I added it back, which is the same as doing nothing at all, right? Because if I combine like terms here, I get 0, right? So it's equivalent to me doing nothing. Okay. So what I'll do now is I'm going to break this into two pieces with a common denominator. What do you notice in the first fraction? You have a greatest common factor of f of x plus h. In the second fraction, what do you notice? Yep. Hi, come on in.
Can I take a few pictures for your book?
Yeah, everyone's really happy at me right now, so it's a great day to do that.
No. Thank you.
You're welcome.
Yeah.
Oh no. Mr. Kulik, did you goober this? Shoot. No, I think I just picked the wrong thing here. 1 second. Let me think. No, the product rule is right. Your teacher's just dumb.
Wait, I think you just disproved the product.
No, I just picked the wrong thing. I just looked at this the other day. Of course you can. Okay, no, that's right. Oh, sure. Sure. Okay. Everybody's okay? All right. Going to use some limit rules now. Yeah,
Just not like this.
right. Okay. So now we're going to evaluate some of these limits. What's the limit as h approaches 0 of f of x plus h? F of x, right? Because you just plugged 0 in for h, and x plus 0 is x, right? Okay. What do I get when I do the limit as h approaches 0 of g of x plus h minus g of x over h?
0 over h.
Zero.
Oh, indeterminate. I
Like
know.
5? Like
Zero.
that doesn't exist?
No, it's just a zero.
Infinite.
Wait, what?
It's the derivative. That's the limit definition of the derivative for g, is it
Oh,
not?
yeah. Yeah.
Oh, it is.
Oh,
Look
yeah.
at that. That is exactly the limit definition of the derivative. Okay. What's the limit as h approaches 0 of g of x? G of x. And then-
F prime.
And what do we have? The product rule.
That's crazy.
So like, oh my god, I still don't get it.
Oh.
Let's do some numeric example now
Yeah.
to get used to practicing it, right?
Yes.
Okay. So let's look at here. We have a couple of examples. So it says we want to do the derivative of x times e to the x. Notice there's nothing algebraic I can do to get those x's into one place, right? I can't turn this into an exponential. I can't turn it into like some power function. It's two separate functions. There's no way for me to combine them together. So what I'm going to think about, I'm actually going to call this k. So like my f of x is x, and my g of x is like e to the x. Everybody okay with that? So if that's the case, the derivative of k of x is going to be f of x times the derivative of g of x plus g of x times the derivative of f of x. Right? So the derivative of f of x is 1, and the derivative of g of x is e to the x. So my answer then is going to be x times e to the x plus e to the x. The derivative of e to the x is e to the x. Always. Yep. Yeah. Certainly. Okay. So part B says to find the nth derivative of f of x. So let's look what happened here. In other words, we found that the derivative of k of x is k of x plus e to the x, right? That's kind of what happened. You got the same thing over again plus an extra e to the x. So what would we expect the second derivative to be? Well, I'd get a k to the x plus e to the x when I differentiate this, plus another e to the x. Well, because we saw that when I do the derivative of k of x, I get it back plus the e to the x, right? So when I do the second derivative, I just get another k of x back. Well, let's do it this way. That this piece gives me those two, and then that piece just stays the same when I take the derivative of it. Who sees the pattern? What's the nth derivative going to be? Yeah, that's right. That's the pattern you should see. That each time the k to the x stays there, but you pick up an extra e to the x every time you take the derivative. That's the pattern they were hoping you to see. Let's do another numeric example. Here we're told f of t is equal to square root t plus a plus bt. Now, when I look at this, I don't see any reason to use the power property. Or the product rule, I should say. I can do this just using the power rule, right? If I distribute the root t through, and then I combine like terms, I can now just use the power property, and I think that is easier than having to use the product property, right? Could I have used the product property there? Yes, Pierce.
Oh, wait. No, never mind.
Okay. Sometimes it just takes a minute for it to set in, but if you think I make a mistake, please speak up. I'd hate to go through like a long time and come back like, hey, 10 minutes ago when we're doing this example, are you sure that 2 plus 3 is 6? Be like, well, no, I'm not sure that that's right. I wish you would have said something earlier because I would have corrected it. So just to show you that every time you see multiplication doesn't mean that you should pull out the product property. You could, but it's much in the same way like if you see a fly, you don't need to pull out your handgun to kill it. You can just like swat it with the phone book, right? Like it's too powerful of a weapon for what it is you're trying to use it on. Much like the product property here is too powerful of a weapon for what you want to use it. Will it work? Sure. But like, I wouldn't use it to do that. So far, so good?
I have one question.
Yeah.
So like, how come we don't like, because it's like a square root to the denominator, like how come we don't?
Care about that anymore?
Yeah.
Because it's just makes things worse. In general, my rule for you would be, if it's a variable under the radical, and that's what's in the denominator, don't worry about it.
But if it's like 2 root like 3.
Then you could worry about it. And I would say at some point your math teacher is going to tell you to stop worrying about rationalizing your denominator. I would say like we're pretty close to that point right now. If you don't hear it in your Calc 1 classroom in college, it'll be in your Calc 2 or 3 Calc classroom. Someone will eventually tell you stop worrying about rationalizing denominators. We don't care anymore. This question here is another very, very common AP question format. If f of x is equal to the square root of x times g of x, and we're told that g of 4 is 2, and g prime of 4 is 3, find f prime of 4. So again, I would start by rewriting the square root of x as x to the 1/2. And I'll do the derivative of f. So that's going to be f of x times the derivative of g plus g of x times the derivative of f. Oops, negative half. So far, so good? Absolutely. Sure. And now if I want f prime of 4, I'm just going to go ahead and plug 4 in for my x's. So 4 to the 1/2 is 2. G prime of 4 is 3. G of 4 is 2. And then here's the $100 question. 1/2 times 4 to the negative 1/2 is? So 4 to the negative half is 1/2. And 1/2 times 1/2 is 1/4. So what do we get here? We get 6.5. Emma? How did I get what? This? That? I did the derivative of x to the 1/2. So I did the power rule. So the 1/2 times x to the 1/2 minus 1. 1/2 minus 1 is negative 1/2. You're still making some faces. Do you see it or no? So I'm doing that, right? Because the formula is f times the derivative of g, and then plus g times the derivative of f. So that's what I did there. Is that okay? Pierce?
So how come for like x's you plugged in 4? Oh,
Because the problem asks for f prime of 4. Everybody's okay with this? And what this does is it forces you to use the product rule, right? Like you can't algebra your way around this. There's no tricky algebra to be done. You must use the product property here, or the product rule, I should say. Next up, what if I want to divide two functions? Like if I have x divided by e to the x. Again, there's no algebra I can do to combine those x's into one place. So I can't use the power property in that sense. I have to use what we'll call the quotient rule. So what the quotient rule says, if I have some function f of x divided by g of x, the derivative of that is going to be g of x times the derivative of f minus f times the derivative of g all over g squared. I'm not going to do the proof of this today because it's more time consuming than I want it to be, but it's the exact same trick as the previous one. So I set it up the exact same way and I subtract the exact same thing. It's just more algebra, but it looks exactly like the previous proof. Pierce.
So in that, like it could be, it's the same thing if you write it as g of x times f prime of x.
Mm-hmm.
Okay.
Yep. Yeah. Yep. So again, remember that this is the same thing as like f prime of x, right? That notation is interchangeable. And a lot of textbooks would just write it like, would do like f over g prime is g f prime minus f g prime over g squared. We'll just write it that way. I see that notation quite frequently. It says the same thing as the product rule above. It's just using primes instead of ddx's because those two symbols can be used kind of interchangeably. All right, let's do some product rule examples, yeah? But just again, think about how big of a hassle something like this is that we're about to look at. How big of a hassle would that be to use the limit definition? It's going to be an incredible nightmare, This we can do in like a relatively small spot. So for the product property, I'm going to think about this as like f of x over g of x. And anytime it's kind of looks a little bit complicated, I'm going to do this like piecewise together, or piece in pieces, and then put it together at the end. So I'm going to just identify the numerator as f and the denominator as g. And the derivative of the numerator is excellent. And the derivative of the denominator is 3x squared. So y prime is going to be g times f prime, or the derivative of f, minus f times the derivative of g all over g prime, or g squared. Oh, yes, thank you. I wrote the wrong thing. Now, is this the way this answer is going to look in the back of the book? No, what are they going to do? Well, there's no solving because it doesn't equal anything, but they're going to simplify, particularly the numerator. The denominator, I doubt they're going to do anything to, but the numerator, they're going to FOIL out and combine like terms.
But you could leave it like that. It's still correct.
If this was a free response question, I would not mark you wrong if you got to that point. Now, if you went and continued and you simplified something incorrectly, I would mark points off for doing that.
Basically leave it like this.
So on a free response setting, the AP would accept that as a final answer. If it was a multiple choice question, this would not be one of the options. They would have the FOILed out and simplified result. So I'm going to go ahead and do that now. In a free response, again, in a free response setting, I would not require that from you. But if it was a multiple choice question, I would not have that as one of your multiple choice options. Fair enough? Okay. Oops. So what am I going to have here? I'm going to have negative x to the fourth. And then I'm going to have negative 2x cubed, then plus 6x squared, plus 12x plus 6. So that would be like your multiple choice answer. Again, if it was a free response question, I wouldn't mark you down for what we had before, right? The calculus is done. I would say when the calculus is done, you can be done in a free response setting. Although if it was a multiple choice question, that would not be one of the responses. Hello. Thanks. Trader, that's yours. All right, let's do another. So it says find the equation of the tangent line to the curve, yada, 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 at this point, yada, yada. Okay, so if I want the equation for the tangent line at a certain point, all I need is the slope at that point, correct? To get that slope, what am I going to need? The derivative. So the derivative of y prime, again, I'm going to think about this as numerator and then denominator. Yep. The derivative of e to the x is, and the derivative of 1 plus x squared is. So y prime is going to be g of x times f prime minus f times g prime all over g of x squared So the m we're concerned with is y prime of 1. Notice I'm not simplifying that anymore because it doesn't ask me for what is the derivative. It asks me for the tangent line. I can plug 1 into this just as easily as if it was simplified down. Don't bother simplifying something if you're just going to plug a number into it. So just plugging 1 in for my x's. So I have in the numerator 2e minus 2e over 4. So the slope there is 0. Pierce?
You're doing for y, you're plugging in 1.
Mm-hmm.
Get 1.
Because I know that I want the slope at that point. So I'm using the x from that point. Is e to the 1 what? E to the 1 is a constant. That's like the number 2.79. I don't remember what it is. So there's our slope. So if I want to write the equation for my tangent line, that's it. The slope is 0, it's a horizontal line, so it's just y equals, and then the y coordinate. Don't have to muck around with anything else. So far, so good? Okay. This is just a summary of the derivative rules we've seen to this point. We've just written them in a compact way. So again, do you need this for anything? No, but it's nice to having it all in one place, right? So this is everything that we've done. So derivative constant, 0. Power rule, derivative exponential, the constant multiple rule, sum rule, difference rule, product rule, quotient rule. Should you have these memorized? Yes. Would I ask you to write them down on the test? No. Do you need to be able to use them fluently? Yes. So you just need to have them memorized well enough to where you can use them effectively. Elena.
Do you think when they test this, there's a lot of help that are asking us to use the notation, or do you think more often than not we can use the shortcuts?
Massively more often than not, you would use the shortcut. They'll ask you to evaluate limits, like give you like what is the limit of yada yada yada. It wouldn't say do the derivative of this using the limit notation.
In fact, it's evaluate limit using
You can
these.
you can do the derivative using these. The limits you have to use like your limit rules, or in a certain circumstance, we can use derivative rules to do a limit. Let me show you an example. Let's do this. So we know this is true, right? That's one of our derivative rules, or definitions of a derivative. So for example, I should actually say this is like f prime of a. Thanks, Tessa. So let's say I had something like this. So Elena, what I would hope that you might notice here is this starting to look a lot like the definition of a derivative. So what I would want to check here is 77 equal to f of 7? i.e., is it 7 squared minus 4 times 7? Which it is. So how am I going to do this limit? This is just going to be the derivative of x squared minus 4x evaluated when x equals 7. I'm not doing any limits here. I'm just going to say, oh, I recognize this is actually just a derivative evaluating at a point. Let me just do it that way. So this would be like 2x minus 4 evaluated when x is 7. So 14 minus 4 is 10, and I'm done. Right? Like, isn't that lovely? Now, could you have done that here? No, because if you plugged in 7, you're going to get 0 over 0. But I could recognize it as a derivative and avoid having to do limits at all. Like, oh. So that kind of question would for sure would end up in an AP, particularly like that's a multiple choice question, is what that reeks of to me. Because hopefully now it's checking that you know the limit or the derivative, the limit definition of a derivative. It's getting you to use it in kind of an unexpected manner that lets you do it in a massive shortcut. But it's still accessible to do that limit without recognizing that. It just stinks. Like it's just a time eater. Yeah, that's a lovely, lovely shortcut. That might even be something I might ask you to be able to do on the test. Since I'm not going to ask you to do the definition of a limit directly, I might ask you like an indirect way where you need to use that limit definition of a derivative to do a problem. Yeah, you recognize that this is just the definition of a derivative at a point. And rather than using the limit to get that, I just can use my derivative rules to get the derivative and plug the point in. Which is like, compared to... Yeah, so what I recognize is this is just, this thing is just the derivative of that evaluated when x is 7. So like, let me just do that. I have a better way of doing that than doing the limit, because now I have all these nice derivative shortcuts. They don't need to do the limit.
Did you make us do it on a test?
I think that this kind of a problem is super fair for me to ask, because at no point did I actually do a limit. Really. Like I did the derivative and that was the answer to this limit, which is, I think, pretty okay. Emma. Well, you're recognizing that this looks like, that form. So what I would want to check is f of a 77 if f of x is this? So that's what I did down here. I checked, okay, is 77 equal to f of 7? It sure is. So all I'm doing here is doing a derivative for that f of x when x is 7. Yeah. Does that feel better though? And you see like, oh, that's a nice limit shortcut trick. Now, does that work for every limit? No, only ones that are set up that they look like a derivative. But like if you get a weird limit on an AP exam where you're like, how the heck am I supposed to do this? Like this is your trick. Yes, Elena.
This is off topic.
That's okay.
Like on the homework, question 2, it says solve or find the derivative in 2 ways by using the quotient rule and by simplifying. What does it mean? Simplify.
So like doing algebraic simplification so you can use the power rule.
Oh,
So like
don't actually use the power rule.
So like you remember how on this example 2, I showed you how you could just do the power rule with this if you did a little bit of algebra first? That's what they're asking you to do. Do that, and then also do the power rule or the product rule to show that you can do it both ways. That's all it's asking you to do. It's like a problem like this, and it's like, do it the smart way and then do it the dumb way and prove to yourself that like both work, and they're like, maybe one seems like less work than the other.
Would you have us do it like that on the test?
No!
Okay, good.
Isabel,
Perfect.
what's up?
Oh, it's limited.
Sure. You're welcome. So in general on the test, we can talk more next time, but I won't ask you to do the limit definition of a derivative, to find derivatives, unless like for some reason it's like necessary in that problem. Like that limit thing I just showed you, I think that's a super fair question where you kind of need to know the definition of the derivative to do that effectively. Particularly if that's like a multiple choice question without a calculator. Like good luck doing that limit without, I mean, you're like, oh, I just build a table for that. And that's not bad. It's like, it's pretty bad if you try to build the table by hand or looking at the graph. It's like, well, good luck graphing that by hand. Like that stinks. Elena.
Would you recommend using the quotient rule?
So here's what I would tell you. If your denominator is a monomial, like a single term, you can probably get away without using the quotient rule doing algebra.
Excuse this interruption.
Otherwise,
For
you definitely need to use the
freshmen
quotient
community
rule.
time rooms, you need to proceed immediately to the Grimaldi. Bring your backpacks with you, and you'll leave them in the Grimaldi off to the side. Again, freshmen, after this hour, please proceed immediately to the Grimaldi. Thank you.
So what would you do with the vote? Which is like number 5 is x over 2x. Would you recommend just like
You could do that as a,
combine it?
yeah, you'd have to do that as a quotient
Straight
rule.
to- okay.
Yep, have to do it as a quotient rule because there's no way to combine the x and the e to the x.
That's what I was thinking.
Yes.
Just didn't know if I was like.
So just as a reminder, if you wanted to start on those MyAP questions, everything is up. It's in, I have the paper version in the OneNote, but if you'd rather do it on the computer, so the computer checks it on your own and you don't have to check it yourself, the multiple choice questions are assigned as a homework quiz or as a quiz on the MyAP. You don't need to do it. I recommend you do. You're a fool not to do it. But whether you do it in the site or on paper on your own makes no difference to me.
Is that the same?
They're the same problems, yes. Cool? Okay. Have a great day, guys. Oh, you guys have a minute.